It is the world's most famous equation. Let's see how Einstein came up with E equals mc squared. In 1905, Einstein published 4 groundbreaking papers, and for the first one he was awarded the Nobel Prize for Physics. The third paper is where Einstein proposed the special theory of relativity, and in that paper he detailed the postulates of relativity and derived detailed equations for the effects he was proposing. But a few weeks later he published a short follow-on article which used the results of special relativity to explore a new idea. It is in this paper that Einstein showed that mass and energy are equivalent and linked by the speed of light. Now, there are many ways of deriving the E equals mc equation, but we are going to actually follow how Einstein presented it in his paper. This article is usually known as the mass-energy equivalence paper, and it is only 2.5 pages long. Interestingly, it does not actually contain the term E equals mc squared in this form. That would come later, but in this article Einstein used slightly different terminology, as we will see. In this paper, Einstein does not give each step of his calculations, which is why the paper is so short, but we will go through the steps so it is clear how Einstein arrived at the E equals mc squared result. In these mathematical steps, there are equations which we will have to rearrange and work on, and we will not dwell on those, but feel free to pause the video if you'd like to follow the steps in more detail. The paper is entitled, "Does the inertia of a body depend upon its energy content?" So it does not include the word mass in the title, but its proposal was that mass and energy can be considered to be different forms of the same thing. Einstein used the term inertia as Isaac Newton had done in his laws of motion, with inertia being the property of a body which causes it to resist being accelerated. So the more mass a body has, the more inertia it offers to being accelerated by a force. In the first line of the paper, Einstein says that the results from the previous investigation lead to a very interesting conclusion. The previous investigation he's referring to was the special relativity paper. So this mass-energy equivalence paper just deals with one idea that Einstein had after he'd published the special theory of relativity. He reminds us of the postulates of special relativity and then assumes that we are familiar with the results from the special relativity paper. So the mass-energy equivalence paper starts where special relativity left off. The key result from the special relativity paper that Einstein relies on was presented like this, where Einstein derived an equation for how frequencies of light are seen from 2 frames of reference. This is really the derivation of the well-known Doppler effect, but taking into account relativistic motion. There is one more thing which is important to note about the frequency of light. In 1900, Max Planck had shown that the energy of light is related to its frequency by a constant, which we now call the Planck constant. Because energy and frequency are linked to each other, Einstein used this Planck relationship to substitute energy for frequency in the equation from his special relativity paper. Frequency can be directly replaced by energy, and Planck's constant cancels out because it is on both sides. So this was Einstein's starting point. He presents the equation for how energy is seen in 2 frames of reference. In this equation, Einstein was keeping things very general, where the light was travelling at an angle phi, but to keep things simple here, we will just use the case that the light beam is moving such that cos of phi equals 1. Hence the equation for energy, L star, simplifies to the one shown in the yellow box. This is what we will use from now on. Einstein then proposed a thought experiment. Imagine there are 2 bodies. Body A is at rest and body B is moving at constant velocity v. So these bodies are in inertial frames of reference. The kinetic energy of body A at the start is called E0 in its own frame of reference. The kinetic energy of body A as seen from body B's frame of reference is called H0. So E0 and H0 are the energies of body A as seen from A and B respectively. Body A then emits two pulses of light in opposite directions, and each pulse of light has an energy L/2. On emission, body A remains at rest with respect to body B. Now, after emission, body A's kinetic energy is called E1. What Einstein did throughout this thought experiment was to see how the energy of body A is measured by both bodies in their own frames of reference, both before and after the emission of light. The energies which body A measures are called E0 and E1 before and after emission, and the energies which body B measures are called H0 and H1 before and after emission. From the law of conservation of energy, we can say that the total energy before emission must equal the total energy after emission. So we can write E0 equals E1 plus the energies of the two light particles. We also know from special relativity that body B can claim to be at rest and say that body A is moving past it in the opposite direction. So body B does this and claims to be at rest, and then measures the energy of body A. We now use the energy relationship which Einstein started with, which is how the energy of a moving body is measured from the perspective of an inertial observer. As a reminder, body A measured the total energy of its system like this: E0 equals E1 plus the energy of the light. But when body B measures the energy of body A, we get this expression. Here we have H0, which is the kinetic energy of the body before emission, and this equals H1, the kinetic energy of the body after emission, plus the energies of the two light particles which are emitted. The energies of the light particles have been modified due to their motion according to Einstein's earlier expression. So this relationship also satisfies the law of conservation of energy. Note, however, that there are plus and minus signs for the two light particles because they have opposing velocities as seen by B. So this is our equation for the energy of the moving body, and we can simplify this into the following expression. So now we have the energy of the body A as measured both by body A and by body B. We can subtract the E equation from the H equation to get this, and then we can bring E1 and H1 terms over to the left side, so we get this relationship in the white box. We can see that H0 minus E0 is the kinetic energy before emission, and H1 minus E1 is the kinetic energy after emission, so we can say that the difference in kinetic energies equals the energy of the emitted light. We'll call the kinetic energies before and after emission K0 and K1. We also note that we have the Lorentz factor, gamma, present on the right-hand side. This appears everywhere in relativity theory and is seen here because the light particles are moving at a speed v. We can rewrite the Lorentz factor as shown here on the right, and this will be useful in the next step. What Einstein does next is to take the Lorentz factor and do a Taylor series expansion on it. We will not go into what a Taylor series expansion is here, but suffice to say, it is a mathematical tool to express a function in terms of an infinite series of polynomials. The reason why this Taylor series expansion helps will become clear, but Einstein just states the result in his paper. We will, however, show the steps so it's clear what Einstein was doing. The Taylor expansion of the Lorentz factor gives us this polynomial expression in terms of powers of v upon c. This expression keeps going with higher and higher powers of v upon c, but we are only showing the first three terms here. So we started with this expression for kinetic energies, and now we have a relationship for the Lorentz factor bit of it. So we can replace the Taylor expansion into our kinetic energy equation. We see that +1 and -1 appear in two places inside the bracket, so these cancel out, leaving us with this equation. Einstein then states that we can ignore the terms which have powers of 4 and higher because these will be insignificant because the speed of light is so large. Hence, we get a much simpler equation for the differences in kinetic energies. Einstein notes in the paper that this expression is very similar to the equation for the kinetic energy of an electron. And we can see by comparison that L upon c squared is equivalent to m. Hence we can say that m equals L over c squared. And noting that in Einstein's paper, L is denoting energy. So Einstein concludes that if a body gives off radiation L, then its mass reduces by a factor L over c squared. He then generalizes this to say it's true for all bodies, and so the mass of a body is a measure of its energy content. If we take this expression and rearrange it, then we can get an expression for the energy of a body, and this is now in a much more familiar form, although it still uses L for energy. Einstein concludes with the prediction that it should be possible to measure this effect for materials which emit radiation, like radium salts, which were known to give off light at the time. So this is basically saying that if something is radioactive or unstable and it emits radiation, then it should be possible to measure the difference in mass before and after the emission of the radiation, and hence calculate the amount of mass which was involved in creating the radiation. After the publication of the mass energy equivalence paper, Einstein continued to work on this idea and derived the equations in many different ways. Later on in some notes, he did actually replace L with E, so we can see the more famous version of the equation with E equals mc squared. So this is mass energy equivalence. The energy of a body is equivalent to its mass multiplied by the square of the speed of light. Sometimes this mass is referred to as rest mass, denoted by m0, with rest mass being the mass when there is no motion. But m and m0 are generally used interchangeably. Since the square of the speed of light is a really large number, 9 followed by 16 zeros, this means that even a tiny amount of mass contains a huge amount of energy. So even if a body is not moving, so it has no kinetic energy, energy of motion, it nonetheless contains energy due to its rest mass. So the equation E equals mc squared gives us the intrinsic energy of an object due to its mass. Einstein's mass energy equivalence idea paved the way for the nuclear age, where the energy contained in matter could be released. One of the ways which this happens is in the process of nuclear fission. This is where the nucleus of a certain element, like uranium, breaks apart and creates a huge amount of energy as a result of what happens. Fission is the splitting of nuclei, and there are various schemes for doing it, but a typical process goes like this. A neutron hits a nucleus of uranium-235, and this causes the nucleus to become excited and briefly form uranium-236. The numbers refer to the total number of neutrons that the nucleus contains. This unstable uranium-236 then splits into smaller nuclei of barium-141 and krypton-92. If you add 141 and 92, this equals 233. So it is 3 less than the uranium-236 number. Hence, in this splitting, 3 more neutrons are also released to keep the number of particles equal. Nuclear fission, the breakup of the uranium-236 nucleus, is accompanied by the release of a lot of energy according to E equals mc squared. This arises because the total mass before fission is a tiny bit higher than the total mass after fission, and this mass difference is converted into energy according to Einstein's equation. Where the mass difference in nuclear fission comes from is complicated and has to do with how the nucleus is held together, what's called the binding energy, but we won't go into that here. A thing to note is that the 3 extra neutrons which are produced after fission are important because they can then go on to hit 3 more uranium-235 nuclei and hence continue the process, but as a chain reaction, one that multiplies each time. So one fission causes 3 more fissions, which then cause 9 more, and so on. This is how a fission reaction can run away with itself unless it is controlled. Nuclear fission was first demonstrated in 1938 in Germany by Hahn and Strassmann. During the Second World War, both Germany and the USA were developing weapons based on nuclear fission. And as we know, America was the first to successfully demonstrate an atomic weapon. All the nuclear power stations operating today use the process of nuclear fission to generate electricity. Although a large amount of energy is produced by nuclear fission, there are many problems associated with it, especially how to keep the reactions under control to stop things like the Chernobyl disaster from happening. Fission reactions also produce radioactive material, which can remain lethal for centuries, and so it needs to be kept safely stored to avoid contamination. Although nuclear fission produces millions of times more energy than an equivalent amount of coal, nuclear power stations are very expensive to build and have many associated problems. It is hoped that another process called nuclear fusion might one day replace the current nuclear fission power plants, but commercial fusion plants have yet to be demonstrated. In nuclear fusion, 2 isotopes of hydrogen are fused together under high temperatures and pressures, and the result is a nucleus of helium plus a lot of energy. Nuclear fusion also uses E=mc² as the basis for generating energy from a nuclear process. But unlike nuclear fission, it is a far safer and cleaner form of energy. It does not produce radioactive materials, and the reaction cannot run away with itself. So fusion promises an unlimited amount of energy from the most abundant element in the universe, hydrogen, if we can engineer a way of producing it in a controllable commercial power station. So Einstein's 3-page paper from 1905 showed how energy and mass are different forms of the same thing, and Einstein showed how we can derive the iconic equation E=mc². And this is how we will finish our tour of special relativity with the most famous equation in the world. Next time, we will begin to look at how Einstein extended special relativity into what became the general theory of relativity. That contains the concepts of space-time and how gravity comes about, and how we can think about things like black holes and how our universe functions. I hope you've enjoyed our tour of special relativity, and until next time when we embark on general relativity, keep thinking physics.